fields can have many applications. Here just to name just a few. Okay, one of the things is what happens if you put a magnet near an old-fashioned CRT-based TV. CRT, as you know, stands for cathode ray tube. Okay. In a CRT-based TV, you have a beam of high-speed electrons. Okay, a beam of high-speed electrons, which are emitted from the back of the TV. Okay, an electron gun, and they move at high speed. They move at high speed, striking the back of the screen. So here's the CRT tube, causing this part of the screen to be lit. Now we use an electric field to deflect the beam as usual, but this is a beam of high-speed charged particle, right? And you know high-speed charged particles will be subject to a magnetic force if you put a magnetic field in the region. So imagine what happens if you put a bar magnet nearby, near an old-fashioned CRT TV. What's going to happen? You're going to distort the image, okay? Because these beams will travel into different directions because they are now being influenced by the existence of a magnetic field from the bar magnet, okay? And you can easily see that for yourself. Now, this tells us that you do not want a magnetic field, an unshielded magnetic field near a CRT TV. Okay. On the other hand, it is often the case where you put a big honky speaker right next to a TV because you want, you want to get good sound. Usually, the TV itself doesn't produce enough sound. You put a big speaker, actually a whole bunch of speakers sometimes, right? One to the left, one to the right, one above the TV, one below it, whatever. What happens in a speaker? Well, we're talking about conventional speakers, not one of those fancy electrostatic speakers. A conventional speaker, how does it work? Actually, in a conventional speaker, you have the source of a very strong permanent magnet. There is a strong magnetic field. This is because a conventional speaker is driven by a magnetic force. Okay, here's what's going on. You have a permanent magnet which produces a magnetic field inside a speaker. Okay, inside a speaker. Now, a speaker is a device which takes an electrical signal driven by a receiver or an amplifier, whatever, and turns it into audible sound, right? That's what a speaker does. Okay, how does that work? How does that work? Well, in fact, most speakers, in principle, behave like this. You have an electrical coil. Okay, you have a coil which can cause, in which a current can pass through, and this coil, when you connect to a power supply from the source, it will have a variable current going through it depending on the source. As a variable current goes through it, there will be variable magnetic force exerted on it by this magnetic field, right? Which is caused by a pair of permanent magnets. Now, so as for example, if you have an oscillatory motion, say a sound source turned into electrical signal, the current will go back and forth, back and forth, back and forth, and that causes a variable force going back and forth, back and forth, back and forth, exerted on the coil. And the coil is attached to what's called a diaphragm. Okay, this diaphragm therefore is going to oscillate back and forth, right? It's going to oscillate back and forth, and the oscillation is totally in response to the magnetic force, which in turn is proportional to the current, which in turn is proportional to the signal that drives it. So, as you speak into the microphone turns your sound signal into an electrical signal, which is amplified to produce the current driving the diaphragm. So then the diaphragm starts to oscillate, causing the air around it to compress and decompress, and that is the sound that we hear. So you see, in a conventional speaker, we do need a strong source of magnetic field. Same thing happens in headphones. Okay, headphone really is a miniaturized version of a speaker. So in a headphone, you also have a pair of magnets, okay, because you need to establish a magnetic field. As a matter of fact, good headphones will use special materials which produce a very strong magnetic field. And these fields, the strong field can cause greater oscillation of the diaphragm, and therefore causing a greater dynamic response for the sound input. But anyhow, a speaker has a magnetic field, usually pretty strong, and yet right next to it there is a CRT TV, which does not want a magnetic field nearby. So in order to make them coexist one next to another, you need to provide a shield. Okay, you need to shield your speaker away from shield your TV away from the speaker's magnetic field. So modern speakers are usually designed to be in such a way that it shields its own magnetic field, so that you can put it right next to a TV, CRT TV, nothing would happen. This is an important part of the design of a modern speaker, is to shield itself magnetically, so the magnetic field of the speaker does not leak out. Okay, now another useful application of a magnetic field we apply to a moving charge is so-called a velocity selector. When you have a bunch of charged particles flying through a certain region, sometimes, actually most of the time, the particles, each particle have a different speed or different velocity. Okay, different velocity. And yet sometimes, in order to study the behavior of such particles, we must know the velocity. We must separate a particular velocity that we desire from particles moving with other velocities. Now, how do we select a particle moving only with a given magnitude and direction of velocity? Well, we can make use of what's called a velocity selector. Basically, there is a long and narrow channel. Okay, and you got a whole bunch of particles moving in. Now, if you don't do anything, these particles would, with whatever speed, as long as you travel in this direction, they can keep on going through. Nothing would happen. Nothing can stop them. What you do, though, is to expose this particle to a cross of E field and B field. So you put a mixture of E field and B field together. E in this case points downwards and B points into the page. They're perpendicular to each other. We design it like that. Okay, now let's see what happens to a positively charged particle as it makes its way through this region which is filled with both an E field and a B field. Okay, it is a charged particle, therefore there is an electric force on it. And the direction, assuming Q is positive, the direction of the electric force, of course, is downwards, right? It's downwards. It's along the direction of the electric field, of course. It's downwards. How much is that? It's Q times E, right? Magnitude is Q times E. Meanwhile, it is also moving, so it is also exposed to a magnetic force. That's QV cross B. V is like that, B is like that. Okay, I'm sorry, B is inward. So V cross B, you see, it's up. So the magnetic force, however, is Q, V, B. That's the magnitude. Now, usually, if you just put any arbitrary value of the speed, okay, then usually QVB is not equal to QE, right? I mean, you're not that lucky usually. QVB usually is not equal to QE because you put an arbitrary speed. It's not going to work. But if QVB is not equal to QE, then one of them has to be greater than the other. Let's say the magnetic force is greater than the electric force. And as a result, it's going to go up, right? The particle is going to go up. As it goes up, it will be absorbed by the edge of this tunnel. It cannot make its way through it. On the other hand, if the electric force is greater than the magnetic force, then it's going to go bent downwards, and there again will be absorbed by the side of the tunnel. It cannot make through. And the only particle that can successfully pass through this is a particle that moves with such a speed that these two forces just happen to cancel each other out. Okay, so there is no net force on it, it just keeps on going. Okay, so the only particle that can move through is a particle that is subject to the same amount of electric force and magnetic force. QE has to equal to QVB. Okay, now most particles do not satisfy this unless we're looking at a particle whose speed satisfies this equation. You cross out E and you find V is equal to E over B. Only a particle whose speed is like this, is E over B, can make its way through the tunnel without being absorbed. This is how we select a velocity. We can tune the E and B field such that E over B is the speed that we're looking for. Then we expose this bunch of particles to this E and B cross field. Only a particle moving with this speed can make its way through. This is called a velocity selector. Alright, now our example goes on and on. The next example is also very useful in both physics and chemistry. It's called a mass spectrometer. Okay, what this thing does is that, among other things, it can tell you, okay, what is the mass of a charged particle? What is the mass of a charged particle? And that sometimes is very important in chemistry, because in chemistry we may encounter different isotopes. They will have different masses, okay, different masses, yet they have the same chemical behavior. Now, here is how a mass spectrometer works. First of all, we have particles moving at a certain speed, a certain velocity. Okay, we can use a velocity selector. We can pre-select them so that by the time they enter a region filled with a uniform magnetic field, we know exactly how fast they're moving. Okay, the velocity selector. Now, imagine there's a B field going into the paper, uniform B field, and you have a positively charged particle coming this way, perpendicular to the B field, in the plane of this paper. What's going to happen? Well, it's going to be bent by the B field, right? Without changing the speed, but it will be bent. Q V cross B. V cross B. V goes like this and B goes like that. You get a force like that. So a positively charged particle will be going this way. A negative charged particle will be going that way. And a particle that is not charged at all will just simply go forward. Okay? So we can tell by the direction of bending, we can tell whether the thing is positively charged or negatively charged. Now, since we left more space here, let's assume the particle is negative so that it bends around like that. Okay, now you can see clearly that upon entering the field, okay, upon entering the field, this line is perpendicular to the direction of motion. So here is a 90-degree angle, right? So as it turns around, it's going to form a semicircle, exactly half a circle, before it strikes this plate again. Okay, before striking this plate again. So this is half a circle. What is the radius of that circle? Well, didn't we calculate that before? Right? We found it was equal to what? Going back, mv over qb. See that? mv over qb. So I'm going to copy that. Okay, the radius of that circle, r, equals mv over qb. Right? And from that, we can calculate the ratio of q over m, charge to mass ratio, and that once again is v over rb. We said that if we can measure V, R, and B, we can find the charge to mass ratio, we can uniquely identify this particle, and in particular, if we know the charge, we can figure out its mass. That's why we call it the mass spectrometer. Okay, now, V is chosen by the velocity selector. B, we know. What about R? The radius. How do you find R? Well, simple. Look, this is a semicircle, exactly half a circle, so therefore this must be the radius, right? So suppose the particles land somewhere here, so you put a film here, there will be an exposure here, and then so this is where it lands, and this distance therefore must be equal to what? 2r. It's the diameter, right? 2r. So by measuring this distance, you can find the radius, which you plug in here, you can get the charge to mass ratio. Okay, and in particular, if you have a bunch of ions belonging to the same chemical composition, so they have, let's say, oxygen ions, okay, but you have different isotopes. You know, you have oxygen 16, you have oxygen 17, for example. The oxygen 17 is slightly heavier than oxygen 16. So actually, so as they make their way, you will find that they will not land exactly at the same spot. Okay. The heavier particles, where would it land? Look at this. The heavier particles, the more massive particles, will have a greater radius if everything else is the same, right? Same V, same B. So you'll see then two areas of concentration. This is where you got oxygen 16. This is where you got oxygen 17. See that? Okay. So this device can allow you to figure out what kind of isotope oxygen has, for example. This is called a mass spectrometer.